I want you to go outside tonight and look up, not through a telescope, not through any instrument at all. Just look up with the eyes you were born with at the stars that have been above every human who has ever lived, at the same sky that Homer described and that Galileo pointed his first telescope toward, and that the Apollo astronauts looked back at from 250,000 miles away. Look at those points of light, which have been the most constant feature of human experience since before we were human. Now I want to tell you something about what you are seeing that changes the experience completely, not metaphorically, physically, precisely, in a way that follows directly from the speed of light and the distances to stars and the timescales of stellar evolution, all three of which are now known with extraordinary precision. Most of the stars you can see tonight with your naked eye are already dead. Not all of them. The Sun is middle-aged and stable. Alpha Centauri, the closest star system to ours, is probably still burning. But many of the brightest, most prominent stars in the night sky, the ones that define the constellations, the ones that navigators have used for thousands of years, are so far away that the light reaching your eyes left them hundreds or thousands of years ago. And stars change on those timescales. Some of the stars you are looking at tonight have already exploded into supernovae. Some have expanded into red giants that have swallowed their inner planets. Some have collapsed into white dwarfs or neutron stars. The light you are seeing shows you what they looked like when the light left them. It tells you nothing about what they are doing right now. The night sky is not a map of the present. It is a map of the past. Every point of light is a message from a different historical moment, sent from a different distance, gloating at your eye tonight after a journey that lasted from a few years to millions of years to, in the case of the faintest smudges visible to the naked eye, more than 2 million years. The sky is a temporal archive, a simultaneous display of hundreds of different moments in cosmic history, arriving at your retina all at once, indistinguishable from each other in terms of time. This is one of the strangest and most underappreciated facts about observational astronomy. And I think understanding it fully, not just knowing the phrase, but actually internalizing what it means for every specific star you can see, changes the experience of looking at the sky in a way that is both humbling and profound. Let me start with the nearest stars, because they are the easiest to grasp, and because even the nearest stars make the point with striking force. The closest star system to our own is Alpha Centauri, a triple star system approximately 4.37 light years away. The light you see from Alpha Centauri tonight left that system 4.37 years ago. If Alpha Centauri exploded in a supernova tomorrow morning, we would not know about it until 4.37 years from now. The explosion would happen, the star system would be destroyed, and we would be completely unaware of it for more than 4 years. The night sky would show a bright new star appearing one morning, but the event that created it would have occurred more than 4 years earlier. 4 years is short enough to feel almost real. You can think about what you were doing 4 years ago. You can remember specific events from 4 years ago. Alpha Centauri, the closest star in the sky outside our solar system, is showing you what it looked like when those events were happening. That is close enough to the present to make the light travel time effect tangible. Now move to the bright stars that define the familiar constellations. Sirius, the brightest star in the night sky, is 8.6 light years away. The light arriving tonight left Sirius 8.6 years ago. Vega, one of the stars of the Summer Triangle, is 25 light years away. The light from Vega tonight left 25 years ago. Arcturus, the bright orange star in Boötes, is 37 light years away. Capella in Auriga is 43 light years away. Rigel, the brilliant blue-white star in the lower right of Orion, is approximately 860 light years away. The light from Rigel you see tonight left during the 12th century when Genghis Khan was building the Mongol Empire. That number, 860 light years, is worth pausing on. Rigel is one of the most luminous stars in our galaxy, roughly 100,000 times more luminous than the Sunday. It is a blue supergiant, a type of star that burns hot and fast and lives for only a few million years before exploding as a supernova. It is already close to the end of its life, and the light you see from it tonight was emitted 860 years ago. The Rigel you see is the Rigel of the 12th century. What Rigel looks like right now, in whatever state it currently occupies, will not be visible from Earth for another 860 years. Betelgeuse is the most famous example of a star that may already be dead. The red supergiant in the upper left of Orion is approximately 700 light years away. It is one of the largest stars in our galaxy, so large that if it were placed at the center of our solar system, it would extend beyond the orbit of Jupiter. It is nearing the end of its life. Astronomers estimate it will explode as a supernova within the next 100,000 years, possibly much sooner. When it does, it will be visible in daylight for weeks or months, brighter than the full moon. And here is the critical point. It may have already exploded. The light from the explosion might be on its way to us right now. Or it might have exploded 50 years ago, and we are still waiting for the light to arrive. We cannot know. From Earth's perspective, Betelgeuse is a point of light that we see as it was 700 years ago. Whatever it is doing right now, in the early 21st century, by the calendar of our solar system, is invisible to us and will remain invisible until the light from those events arrives 700 years from now. The famous dimming event that Betelgeuse underwent in late 2019 and early 2020, when it faded to 1/3 of its normal brightness and triggered widespread speculation that it might be about to explode, was an event that actually happened around the year 1320. It was not happening as we watched. It had already happened 700 years before we observed it. The star that appeared to be dimming on our telescopes had already recovered from whatever caused the dimming centuries before our instruments detected it. The event we observed in real time was, in the reference frame of our solar system, historical. Now let me extend this to the objects visible to the naked eye, but not as individual stars. The Andromeda Galaxy, designated M31, is the most distant object clearly visible to the naked eye. On a dark night, away from city lights, it appears as a faint smudge of light in the constellation Andromeda, roughly the apparent diameter of the full moon, though vastly fainter. The light you see from Andromeda tonight left that galaxy approximately 2.537 million years ago. 2.537 million years. The light arriving at your eye tonight, after traveling through the void between galaxies, was emitted before the first stone tools were being fashioned on the African savanna, before Homo habilis existed, before the genus Homo existed at all. The hominids who were alive when that light left Andromeda were not anatomically modern humans. They were earlier members of our evolutionary lineage, with smaller brains and more primitive behaviors. The light has been traveling through intergalactic space, carrying information about the state of a galaxy containing approximately 1 trillion stars for 2.5 million years, and it is arriving at your eye tonight. What is Andromeda doing right now? We have no idea. We cannot have any idea. The Andromeda you see tonight is the Andromeda of 2.537 million years ago. Whatever Andromeda looks like at this moment in the early 21st century, we will not see it until roughly the year 2,502,537 CE. By then, if any descendants of humanity still exist, they will be viewing with eyes or instruments not yet imagined, from perhaps a very different location in the galaxy, a universe that has had another 2.537 million years to change. The Andromeda Galaxy is on a collision course with the Milky Way. The two galaxies are approaching each other at approximately 110 kilometers per second and will begin their first gravitational interaction in roughly 4.5 billion years. This is not a hypothetical. It is as certain as orbital mechanics allows us to be. But the Andromeda we see tonight is the Andromeda of 2.537 million years ago, at a distance of 2.537 million light years, approaching us at 110 kilometers per second. It has been approaching for those entire 2.537 million years since the light we see tonight was emitted. The Andromeda of right now is 2.537 million years closer to us than the Andromeda we see tonight. This temporal displacement grows with distance in a way that is precise and calculable. The Large Magellanic Cloud, a satellite galaxy of the Milky Way visible from the southern hemisphere, is approximately 160,000 light years away. The light arriving tonight left 160,000 years ago, when modern humans were just beginning to spread out of Africa. The Small Magellanic Cloud is approximately 200,000 light years away. The Triangulum Galaxy, M33, the third large member of our local group, is approximately 2.73 million light years away, slightly farther than Andromeda. Its light is arriving from before Homo habilis. With a modest amateur telescope, you can see galaxies in the Virgo cluster approximately 54 million light years away. The light arriving tonight from those galaxies left when the Eocene epoch was just beginning, when early primates were first appearing in the fossil record tens of millions of years before any hominid existed. The largest galaxies in the Virgo cluster contain trillions of stars, and you are seeing them as they were during the age of early mammals. With larger telescopes, professional instruments, the distances extend further. The Hubble Space Telescope and James Webb have imaged galaxies at distances of billions of light years, billions of years in the past. The most distant galaxies detected by James Webb, with redshifts above 13, are being seen as they were when the universe was only a few 100 million years old, less than 3% of its current age. The light from those galaxies has been traveling through an expanding universe for more than 13 billion years. Now let me take the argument to its most specific and most personally significant form, which is the question of what specific stars you see tonight are actually still there. Not in the philosophical sense of asking whether light from the past tells us anything about the present. In the concrete, empirical, stellar evolution sense of asking, given that star's type, its luminosity, its mass, how long does it live? And given how far away it is the light travel time long enough that the star might have ended its life before the light now arriving at your eye was even emitted? The answer depends on the type of star. Different stellar types have dramatically different lifetimes, ranging from a few million years for the most massive blue supergiants to more than 10 trillion years for the least massive red dwarf stars. The most massive stars, blue supergiants with masses more than 20 times the Sun's mass, live for only a few million years before exploding as supernovae. These are the hottest, brightest, most luminous stars in the galaxy, visible from enormous distances because of their extraordinary luminosity. But precisely because they are so luminous and so massive, they burn through their hydrogen fuel rapidly and die young. A blue supergiant star that is 10,000 light years away has a light travel time of 10,000 years, which is a small fraction of its few million year lifetime. It probably still exists. But a blue supergiant 100,000 light years away has a light travel time comparable to its entire lifetime. We might be seeing the light from a star that exploded while the light was still in transit. In practice, the brightest stars visible to the naked eye in our own galaxy are mostly within a few thousand light years, and their light travel times are short compared to their lifetimes. But the Milky Way is full of blue supergiant stars visible in the plane of the galaxy, particularly in the direction of the galactic center, and many of them are tens of thousands of light years away. Among those distant blue supergiants, there are statistically certainly some that have already exploded. We are seeing them as they were, not as they are. The red supergiant stars, like Betelgeuse, are the second most likely category to have already changed their state by the time their light reaches us. Red supergiants are the most massive stars that have not yet exploded, typically with masses between 8 and 25 solar masses. They live for tens of millions of years in their red supergiant phase before exploding. Betelgeuse, at 700 light years, is close enough that its light travel time is short compared to its expected remaining lifetime. It probably still exists as a red supergiant, but there are red supergiants in the Milky Way and in other galaxies that are farther away with light travel times comparable to or exceeding the time scale on which they could have changed state. For the typical bright star visible to the naked eye in the northern or southern sky, the probability that it has already ended its life is low but not zero. For the typical bright star visible to the naked eye in the northern or southern sky, the probability that it has already ended its life is low but not zero. Let me be more quantitative about this. The lifetime of a star depends primarily on its mass. The most massive stars, with masses above 20 solar masses, live for only 2 to 5 million years. Stars with masses between 8 and 20 solar masses live for tens to hundreds of millions of years. Stars with masses between 1 and 8 solar masses, like the Sun, live for billions to tens of billions of years. Stars with masses below 1 solar mass live for tens of billions of years or more. The Sun, with its mass of 1 solar mass, has a total main sequence lifetime of approximately 10 billion years and is currently about halfway through it. The naked eye stars that define the familiar constellations are almost all within a few thousand light years. Their light travel times range from a few years for the nearest to a few thousand years for the most distant bright stars. For stars with lifetimes of billions of years, these light travel times are completely negligible. A star that is 1,000 light years away and has a lifetime of 5 billion years is showing us its state from 1,000 years ago, which is 0.00002% of its lifetime in the past. It is virtually certainly still there. But the most luminous naked eye stars, the blue and blue-white supergiants, have lifetimes of only a few million years. They are the most massive stars in the galaxy, burning their fuel at prodigious rates. Rigel, at 860 light years and with a mass approximately 17 times the Sun's, has a lifetime of roughly 8 million years. The light arriving tonight left 860 years ago. There is essentially no chance that Rigel has changed significantly in 860 years relative to an 8 million year lifetime. Consider the most luminous stars in the Milky Way visible to the naked eye at much greater distances. The hypergiant star Rho Cassiopeiae, at approximately 8,200 light years, is one of the most luminous stars in the galaxy. Stars at its level of luminosity have lifetimes of only a few million years. The light arriving tonight left 8,200 years ago, while civilizations in the Fertile Crescent were just beginning to develop writing and agriculture. Rho Cassiopeiae, with its immense mass and fierce burning, might have changed significantly in 8,200 years. We would not know. And for the supergiants visible in other galaxies, the Milky Way's companions, the light travel times are long enough that even stars with lifetimes of tens of millions of years could have changed state. The brightest blue supergiants in the Andromeda Galaxy are visible with large amateur telescopes and are 2.537 million years away. Blue supergiants, with masses of 50 solar masses, have lifetimes of only 3 or 4 million years. Some of the blue supergiants visible in Andromeda tonight are seeing them in the first half of their lifetimes. Others may be seeing them in the last quarter. The light arriving tonight tells us nothing about which half. It is statistically certain, given the number of massive stars in our galaxy and in the local group, that right now, as you read these words, there are stars in the Milky Way and nearby galaxies that have exploded as supernovae within the last few thousand years, whose light has not yet reached Earth. There are stellar deaths happening right now that we will not see for centuries. The sky we observe is not only a picture of the past, it is missing events that are happening right now, whose announcement is still in transit. The next Milky Way supernova visible from Earth is expected on average every few centuries. The last observed was in 1604, Kepler's supernova in the constellation Ophiuchus, at a distance of approximately 20,000 light years. That supernova actually occurred 20,000 years ago during the Upper Paleolithic, when the Ice Age was approaching its maximum extent. The light arrived in 1604 and was observed by Johannes Kepler and many others, none of whom knew what they were seeing. We have been waiting for the next one for 420 years. Betelgeuse is the most likely candidate, and it will happen within the next 100,000 years, giving us roughly a 50% chance of seeing it within the next 10,000 years. When Betelgeuse explodes, the light and neutrinos from the explosion will arrive at Earth simultaneously to within a few hours, having traveled the same path for the same time. The neutrinos will actually arrive slightly before the optical light, as they did for SN 1987A, because they emerge from deeper in the star and travel slightly faster through the material during the first seconds of the explosion. Gravitational wave detectors may also detect the explosion. For the first time, we will see a supernova in multiple messengers simultaneously, a multi-messenger observation of a stellar death in our own galaxy. That day will come. The light is already on its way for some stellar deaths. For others, the death has not yet occurred, and we are waiting alongside the star in our shared reference frame. The sky holds both messages that are already in transit and stars still burning, whose deaths we will one day observe. Most naked eye stars are within a few thousand light years, and most stellar types live for hundreds of millions to billions of years. The light travel times of a few thousand years are negligible compared to the lifetimes of most types of stars. But the most massive and shortest lived types, and the most distant ones, represent real possibilities for stars that are already dead. Now let me go deeper into the cosmological picture, because the naked eye sky is only the beginning of the story. The universe extends across 93 billion light years of observable volume, and the further we look, the more extreme the temporal displacement becomes. James Webb is currently observing galaxies at redshifts above 13, corresponding to distances of more than 13 billion light years and look-back times of more than 13 billion years. The universe was less than 1 billion years old when the light now arriving from those galaxies was emitted. Those galaxies no longer look anything like what James Webb is showing us. They have had 13 billion years to evolve, to merge with other galaxies, to form new stars and destroy old ones, to build up the structures we see in the present-day universe. The specific galaxies we see in those Webb images have transformed utterly over the 13 billion years since the light left them. Some of the galaxies visible in deep field images from Hubble and Webb no longer exist as distinct objects. They have merged with neighboring galaxies, their stars mixed into larger systems, their individual identities dissolved into the larger structures of clusters and superclusters. Others have been torn apart by tidal interactions with more massive neighbors. Still others have simply run out of gas, their star formation having shut down billions of years ago as they exhausted their supply of cold molecular hydrogen. The light from all of these objects is arriving at Webb's mirror right now, carrying information about their states at specific moments in the past. The detector is receiving photons that began their journey before the Earth existed, before the Sun existed, before the Milky Way had taken anything like its current form. Those photons have crossed billions of light years of expanding space, been redshifted from ultraviolet or optical wavelengths into the infrared that Webb detects, carrying the imprint of the physical conditions at the moment they were emitted. This is why James Webb is specifically described as a time machine, not metaphorically. It literally sees further into the past than any previous telescope. The infrared sensitivity that allows Webb to see beyond Hubble's reach corresponds to seeing objects at earlier cosmic epochs at higher redshifts further from the present. The edge of Webb's observable reach is the edge of the cosmic history we can access with light. Beyond that edge, in an important physical sense, there is nothing we can know about. Light from regions of the universe, more than roughly 46 billion light years away, the radius of the observable universe has not had time to reach us even after 13.8 billion years of travel, because those regions were already receding faster than the speed of light at the moment of the Big Bang, and their light has been racing against an expanding universe the entire time. The observable universe is a sphere centered on us, defined by the limit of how far light could have traveled since the Big Bang. Everything beyond that horizon is, in principle and in practice, invisible to us and will remain invisible. But within the observable universe, every observation is an observation of the past. Every galaxy survey is a temporal survey. Every sky map is a map of different moments simultaneously. The deepest surveys show us a universe at different ages simultaneously, with nearby galaxies representing the universe as it is now, and distant galaxies representing the universe as it was billions of years ago. The cosmological principle, the assumption that the universe is statistically homogeneous and isotropic, is precisely the assumption that what we see at great distances can be interpreted as the early history of the universe rather than a fundamentally different part of the universe. This has a specific and important implication for cosmology. When cosmologists study the large-scale structure of the universe, when they map the distribution of galaxies across billions of light years, they are simultaneously mapping the universe at different epochs. A galaxy survey that extends to redshift 1 is seeing galaxies as they were 7.7 billion years ago at its farthest extent, and as they are today at its nearest. The survey is not a snapshot of the current universe. It is a temporal cross-section, a slice through cosmic history. Now let me take you to the most personal and most existential dimension of this discussion, which is the question of what it means that the light we see from most of the universe is light from things that may no longer exist in the form in which we see them. This is not just a statement about stars and galaxies. It is a statement about the nature of knowledge, about what we can know about the universe and when we can know it. The universe we observe is not the universe that exists now. It is the universe as it was, at a range of different past moments, displayed simultaneously on the sky. Our knowledge of the universe is always historical knowledge, always a picture of the past rather than the present. This would be merely a philosophical curiosity if the universe changed slowly. If the universe were completely static, if stars never changed, and galaxies never evolved, and the cosmos were a fixed backdrop, the temporal displacement of light would tell us nothing we did not already know. The past picture and the present picture would be identical. But the universe does change. Stars are born and die on timescales of millions to billions of years. Galaxies merge and evolve on timescales of billions of years. The large-scale structure of the universe grows on timescales comparable to the age of the universe itself. And the distances across which we observe the universe are comparable to the distances that light travels in these timescales. When we look at Andromeda, 5 million years in the past, we are looking at a universe that had not yet produced the genus Homo. When we look at the Virgo cluster, 54 million years in the past, we are looking at the Eocene universe. When we look at quasars at redshift 6, we are looking at the universe when it was 1 billion years old. The temporal displacement is not a nuisance to be corrected for. It is the source of our most important cosmological knowledge. Let me give you specific historical examples that make this concrete, because the abstract statement is more powerful when grounded in specific cases. In 1054 CE, Chinese and Arab astronomers observed a new star appearing in the constellation Taurus, bright enough to see in daylight for about 3 weeks and visible at night for nearly 2 years. They recorded it carefully. European medieval astronomers, strangely, left almost no record of it, perhaps because the appearance of new stars was theologically inconvenient in an era when the heavens were supposed to be eternal and unchanging. That new star was a supernova, the death of a massive star approximately 6,500 light years from Earth. The explosion itself happened approximately 6,500 years before 1054 CE, meaning the explosion occurred roughly 7,500 years ago during the late Neolithic period when humans were just beginning to build the first cities. The light from the explosion traveled 6,500 light years through the interstellar medium and arrived at Earth in 1054, where it was recorded by astronomers who had no idea what they were seeing. Today, at that same location in Taurus, you can see the Crab Nebula through a small telescope, the expanding debris cloud from the explosion, still spreading outward at approximately 1,500 kilometers per second. The neutron star at the center, the remnant of the original star's core, pulses 30 times per second, one of the fastest known pulsars. All of this is visible today because astronomers in 1054 recorded the location of the new star precisely enough that modern telescopes could find it. In 1987, astronomers detected a supernova in the Large Magellanic Cloud, the nearby satellite galaxy of the Milky Way, approximately 168,000 light years from Earth. It was designated SN 1987A and was the first naked-eye supernova since 1604. The explosion itself occurred 168,000 years ago during the Middle Paleolithic, when anatomically modern humans were just emerging in Africa and Neanderthals still dominated Europe. The light arrived in 1987. And neutrino detectors at Kamiokande in Japan, IMB in Ohio, and Baksan in the Soviet Union detected a burst of neutrinos from the explosion approximately 3 hours before the optical light was detected, consistent with the theoretical prediction that a supernova produces a neutrino pulse ahead of the optical signal. The remnant of SN 1987A is still expanding, and Hubble and Webb have been observing it regularly since the explosion. In 2024, Webb detected the neutron star at the center of the remnant, confirming theoretical predictions about what happens in the core of a massive star when it collapses. An explosion that happened 168,000 years before Webb was launched is being studied in detail by Webb today. These historical supernovae illustrate the temporal archive nature of astronomical observation. The Chinese and Arab astronomers of 1054 were the unwitting recipients of light from an event that happened 6,500 years earlier. The physicists who detected SN 1987A's neutrinos were receiving messengers from an explosion that occurred during the Paleolithic. The astronomers studying SN 1987A's remnant today are examining the aftermath of an event that preceded the invention of agriculture. This temporal archive extends far beyond supernovae. Every type of astronomical observation is an observation of the past. The cosmic microwave background, which I've discussed in detail in the video about the Hubble tension, is light from approximately 380,000 years after the Big Bang, when the universe cooled enough for electrons and protons to combine into neutral hydrogen. The light from that recombination epoch has been traveling for approximately 13.4 billion years, redshifted from optical into microwave wavelengths by the expansion of the universe. The patterns in that light, the acoustic peaks in the CMB power spectrum, carry information about the universe as it was at that specific epoch, 380,000 years after the beginning. Before the epoch of recombination, the universe was opaque. Photons scattered off free electrons so frequently that they could not travel freely. The universe before recombination is invisible to us through electromagnetic observations. We have no light from the first 380,000 years. The CMB is a wall of fog beyond which we cannot see using photons. But we can see through it using gravitational waves and neutrinos. The gravitational wave background, produced by quantum fluctuations during inflation in the very first moments of the universe, carries information from before recombination. Next generation space-based gravitational wave detectors like LISA may eventually detect this primordial background, giving us access to the universe at epochs before the CMB. Neutrinos decoupled from the rest of the universe approximately 1 second after the Big Bang, and a cosmic neutrino background analogous to the CMB should exist, though it has not yet been directly detected due to the extreme difficulty of detecting the low-energy neutrinos involved. These represent the edges of our temporal archive, the limits of how far into the past we can reach using the different messengers that carry information from the cosmos. Light gives us access to everything from the present back to 380,000 years after the Big Bang. Gravitational waves and neutrinos could, in principle, give us access to even earlier epochs. But there is an absolute limit, the Planck epoch, the first 10 to the minus 43 seconds after the Big Bang, when quantum gravity effects were important and our current theories break down. Before the Planck time, our physics cannot reliably describe the universe, and we have no messenger that can carry information from that epoch. The temporal archive of the universe extends from now back to those first moments, and we are reading it with increasing clarity as our instruments improve. The temporal displacement is not a nuisance to be corrected for, it is the source of our most important cosmological knowledge. The fact that light travels at a finite speed means that we can observe the universe at different epochs, can compare what early galaxies look like to what late galaxies look like, can trace the evolution of cosmic structure across billions of years. But it also means that the universe we see is not the universe that exists. The stars you see tonight are images of stars as they were years or decades or centuries or millennia ago. Most of them probably still exist in roughly the form we see, but some of them have changed. Some have expanded into red giants. Some have shed their outer layers as planetary nebulae. Some have exploded as supernovae. The light from those changes is on its way to us, traveling through the vacuum, arriving in the future. The sky is a picture that is constantly being updated, with new information arriving continuously, each photon carrying news from a different moment in cosmic history. I want to close with something that I think is the most personally significant implication of all of this, which is not about cosmology or stellar physics, but about the relationship between observation and reality. When you look at a star, you are not seeing the star. You are seeing light that came from where the star was at a time when the star was in a specific state. The star itself, the physical object, is somewhere else entirely, at the position where it is right now in whatever state it currently occupies. You have no access to that information. The light from the star's current state will not arrive for years or decades or centuries, depending on the star. This is a strange and somewhat vertiginous realization. We are accustomed to thinking of vision as giving us direct access to the world. We look at a chair and we see the chair as it currently is. But the chair is close enough that the light travel time is a tiny fraction of a nanosecond, completely negligible. Extend the same logic to stars and galaxies, and the light travel time becomes significant, then dominant, then comparable to the entire history of the universe. This is a strange and somewhat vertiginous realization. We are accustomed to thinking of vision as giving us direct access to the world. We look at a chair and we see the chair as it currently is. But the chair is close enough that the light travel time is a tiny fraction of a nanosecond, completely negligible. Extend the same logic to stars and galaxies, and the light travel time becomes significant, then dominant, then comparable to the entire history of the universe. There is a specific connection here to the block universe that I have described in earlier videos, and I want to draw it because I think it deepens the significance of what we have been discussing. In the block universe of special relativity, all events at all times exist with equal ontological reality. The past is as real as the present. Future events are as real as past events. The temporal displacement of light, the fact that we observe events at different moments of their history depending on their distance, is a consequence of the block structure combined with the finite speed of light. When you look at Andromeda and see it as it was 537 million years ago, you are accessing a specific slice of the four-dimensional block, the temporal cross-section of the Andromeda region at a specific time in cosmic history. The stars in Andromeda at that temporal coordinate are permanently in the block at those coordinates. The light you are seeing is real information about a real physical situation that exists as a permanent feature of the space-time structure. The Andromeda of right now, the temporal cross-section at the current cosmic epoch, is also in the block. It exists at its coordinates as real as the Andromeda of 2.537 million years ago. But the light from the current Andromeda is still in transit, traveling toward us, expected to arrive in 2.537 million years. The present Andromeda exists in the block. It is just inaccessible to us because the light carrying information about it has not yet arrived. This is the strange situation that the block universe and the finite speed of light together create. The past of distant objects is directly observable because the light carrying information about those past states has already arrived. The present of distant objects is in the block, as real as anything, but invisible to us because the light has not yet crossed the gap. We are surrounded by reality that we cannot access, not because it does not exist, but because the information has not arrived. There is also something profound here about the relationship between observation and causation. We can observe the past of distant objects, but not their present. We can, in principle, influence the future of nearby objects, but we cannot send signals faster than light to distant ones. The cosmic light travel time structure defines a specific causal structure for the universe, determining which events can influence which other events and which events can be observed from which locations. The light cone, the fundamental geometric object of special relativity, defines this structure precisely. Every event has a past light cone, the set of all events from which light could have reached it, and a future light cone, the set of all events it could send light to. Events inside the past light cone are causally connected to the present event and are also directly observable. Events outside the past light cone are causally disconnected from the present event and are also directly unobservable. The observable universe is the interior of our past light cone, expanding backward in time from the present moment at the Big Bang. The stars you see tonight are inside your past light cone. They are observable because they are causally connected to you. The photons they emitted are events that could have reached you, and in fact did reach you. The stars that have already exploded but whose supernovae light has not yet reached you are outside your past light cone at this moment. The explosion is a real event in the block, but it is causally disconnected from you right now. You cannot know about it, not because information is missing, but because the causal structure of space-time forbids it. When the light from that explosion eventually arrives at Earth, the event crosses the boundary of your past light cone, becomes observable, and enters the realm of what can be known. The transition from unknowable to knowable is not a change in the explosion itself. It is a change in the causal relationship between the explosion and you, as the expanding sphere of light from the explosion engulfs your position in space-time. The universe you observe is a construction, assembled from light that left its sources at many different times, from many different distances, all arriving at your eye or your telescope at this particular moment. If light traveled instantaneously, we would have only a snapshot of the universe as it is today, with no direct access to its history. The finite speed of light gives us a time machine. But the time machine works only in one direction. We can see the past of distant objects. We cannot see their present. And we have been broadcasting information about our own present for only about a century since we began using radio transmissions. The radio signals from Earth have been expanding outward as a sphere at the speed of light since roughly 1900. They have now reached a radius of approximately 125 light years from Earth, containing several hundred nearby stars. Any civilization around a star within 125 light years that has a sufficiently sensitive radio telescope could, in principle, detect our radio leakage. They are seeing us as we were between 0 and 125 years ago, depending on their distance. The information about our present state has not yet reached them. The inverse also applies. For civilizations that are more than 125 light years away and have not been broadcasting for more than 125 years, we are completely invisible to each other. Even if both are broadcasting at full power, the signals have not had time to cross the distance. The Milky Way is approximately 100,000 light years across. For any technological civilization that has been broadcasting for 1,000 years, their information sphere has a radius of 1,000 light years, containing perhaps 1 million stars out of 200 to 400 billion in the galaxy. The vast majority of the galaxy is still outside their information sphere. The universe is full of light from things that no longer exist, and possibly full of signals from civilizations that are alive and broadcasting, but whose signals have not yet crossed the gap. The night sky is full of ancient light. It is also full of ancient silence, a silence that does not mean absence, but only that the light has not yet arrived. It is a composite of the past, assembled into a snapshot that looks like a single moment, but actually spans billions of years of cosmic history. The night sky is not what it appears to be. Let me develop the physics of what happens to a photon during its journey from a distant star to your eye, because the journey is more complex than simply traveling through empty space at a constant speed. When a photon leaves a star, it travels at c, the speed of light, through the interstellar medium. The interstellar medium is not a perfect vacuum. It contains gas, dust, charged particles, and magnetic fields that interact weakly with the photon, slightly dimming and reddening the light over long distances. For nearby stars within a few thousand light years, this interstellar extinction is relatively small, though measurable and must be corrected for in precise observations. For more distant stars and galaxies, the extinction becomes more significant and must be carefully modeled. For cosmological distances, the photons are additionally affected by the expansion of the universe. As the universe expands, the wavelength of the photon is stretched along with the expanding space. A photon emitted with a specific wavelength by a distant galaxy arrives at Earth with a longer wavelength shifted toward the red end of the spectrum. This cosmological redshift is not a Doppler effect, though it looks like one in the local approximation. It is a consequence of the photon's wavelength being stretched by the expansion of the space through which it is traveling. The redshift is the primary observational signature of cosmic distance. A galaxy with a redshift of 1 has its light shifted to twice its emitted wavelength. A galaxy at redshift 2 has its light shifted to 3 times its emitted wavelength. The relationship between redshift and distance depends on the cosmological model, specifically on the expansion history of the universe governed by the Hubble constant and the density parameters of matter, and dark energy. For the most distant galaxies observed by James Webb, with redshifts above 13, the light has been stretched by a factor of 14 or more. Photons emitted in the ultraviolet by hot young stars in those early galaxies arrive at Webb as infrared photons, which is why infrared sensitivity was the key design requirement for Webb's mission to see the early universe. The expansion of the universe also means that the distance to a distant galaxy at the time of observation is not the same as the distance it was when the light was emitted. The universe has expanded during the time the light was traveling. A galaxy that emitted light 3 billion years ago, when the universe was 480 million years old, is now approximately 31 billion light years away, even though its light only had to travel across the universe as it existed at that time, which was much smaller. The light travel time of 13.3 billion years and the current distance of 31 billion light years are both correct descriptions of the same galaxy, referring to different moments and different definitions of distance. This has a specific implication for the concept of the observable universe. The edge of the observable universe, the farthest region from which light can have reached us in the 13.8 billion years since the Big Bang, is currently approximately 46 billion light years away in the comoving frame, the frame that accounts for the expansion of space. The light from those regions has been traveling for 8 billion years, but the regions themselves are now much farther away than 13.8 billion light years because the universe has expanded while the light was traveling. Beyond the edge of the observable universe, there is more universe. The total universe may be vastly larger than the observable part. We simply cannot access information from beyond the edge because the light has not had time to reach us. Everything beyond the edge exists, presumably, but its light is still in transit and will arrive at Earth only in the distant future, if anything remains to receive it. Every photon arriving at your eye tonight from the night sky is a time traveler, carrying information from the past into the present. Some of them carry recent news, only years or decades old. Some carry ancient news, millions or billions of years old. But all of them are reporters from the past, describing a universe that has continued to change during the time their message was in transit. The stars you see tonight are already dead. Some of them, not all, but enough to make the sky not what it appears to be. It is not a map of the present universe. It is a display of the universe's history, a temporal archive accessed by the accident of being at this particular location at this particular time with eyes or instruments sensitive enough to receive the ancient light. And that light, those ancient photons, carry within them the most extraordinary story ever told. The story of a universe 8 billion years old, full of stars and galaxies and dark matter and dark energy, expanding from a hot, dense beginning toward a cold, dispersed ending, and containing, somewhere in its middle ages, a small, rocky planet orbiting an ordinary star. on which organisms evolved that could look up at the sky and realize what they were seeing. Go outside tonight. Look up. The stars are already dead. But let me give you one more layer of this, because I think it is the most extraordinary and the least discussed aspect of the temporal displacement of starlight. The light you see from a star is not just old. It carries specific information about the physical state of the star at the moment it was emitted. The color of the starlight tells you the surface temperature. The spectrum tells you the chemical composition, the velocity of the star, and whether it has a planetary system. The variations in brightness tell you whether the star is pulsating or has a companion. All of this information is coded in the photons arriving at your eye, information about the physical state of the star as it was at the time the light was emitted. For Betelgeuse, the light arriving tonight carries information about the star as it was approximately 700 years ago. The spectrum of that light shows a red supergiant with a surface temperature of about 3,600 Kelvin, pulsating with a period of roughly 400 days, ejecting material from its surface in preparation for the supernova that is coming. The photons carry this information faithfully. 7 centuries after the atoms that emitted them were part of the outer atmosphere of a dying star. The remarkable thing is that Betelgeuse is close enough and red supergiants are long-lived enough that the state we see 700 years in the past is probably still roughly what Betelgeuse looks like today. The star has not likely changed dramatically in 700 years, but we do not know that. We are inferring it from stellar physics, from models of how red supergiants evolve, not from direct observation of the current state. The current state of Betelgeuse is, in principle, unknowable to us. We will learn it in 700 years when the light emitted today arrives. This epistemic situation, knowing the past with precision but the present only by inference, is not unique to astronomy. It is a feature of all knowledge that depends on the transmission of information across distance. But astronomy makes it maximally vivid because the distances are so large that the transmission times are measured in years, centuries, millions of years. Astronomy is the science of the past, not the present. Every observation is an archaeological finding, a piece of evidence about what the universe was like at a specific moment at a specific distance. The night sky is not a map of the present universe. It is a display of the universe's history, a temporal archive accessed by the accident of being at this particular location at this particular time, with eyes or instruments sensitive enough to receive the ancient light. And that light, those ancient photons, carry within them the most extraordinary story ever told. The story of a universe 13. 8 billion years old, full of stars and galaxies and dark matter and dark energy, expanding from a hot, dense beginning toward a cold, dispersed ending, and containing, somewhere in its Middle Ages, a small rocky planet orbiting an ordinary star on which organisms evolved that could look up at the sky and realize what they were seeing. Most of them are still there. But the light you see is older than civilization, older than recorded history, older than the human species. You are receiving messages from the past, from objects that no longer exist in the form you see them, sent before anyone was there to receive them, arriving at exactly this moment. That is what the night sky actually is. And it is more extraordinary, not less, for being true. If this changed how you look at the night sky, if the stars look different to you now, knowing what you are actually seeing when you look at them, tell me in the comments. Tell me which star you find most remarkable in this context and why. Tell me whether the idea that Betelgeuse might already have exploded, and we just do not know yet, strikes you as disturbing or liberating. And tell me whether knowing that every observation is an observation of the past changes anything about how you think about knowledge and reality. Subscribe if you want to keep going into the places where the basic facts of physics transform the most ordinary human experience into something completely different.